Hey everyone, and welcome back to What's Going On in the Internet. You know the drill. You bring the curiosity, we bring the insights. I'm Peter Dawell, here to guide you through today's digital jungle.
And I'm Nora, Kane, ready to add some expert insights to the mix.
Today we're diving into a topic that's not just theoretical, but super practical for all you aspiring computer science wizards out there. VLANs and STP.
It's all about building secure, efficient networks, something you'll definitely need to know in your future careers.
I remember struggling with STP concepts in college. The whole spanning tree idea seemed so abstract.
Well, hopefully we can demystify it for our listeners today. You've provided us with some excellent resources.
Absolutely. We've got Wendell Odom's CCNA 200-301 Official Cert Guide, Volume 1, specifically Chapters 8, 9, and 10, which really lay the groundwork.
And we've also got Part 3 of a study guide focusing on implementing VLANs and STP.
Plus, you even included a Do I Know This Already quiz.
Always love a good challenge.
So let's start with a fundamental question from the quiz. What exactly is a VLAN?
The quiz cleverly highlights what a VLAN is not. It's not a subnet, nor a trunk,
but
a broadcast domain.
Right. Think of it like this. Imagine you're designing the network for a large university campus.
You've got different departments, student dorms, faculty offices, all needing access to the network.
You could use separate physical switches for each group.
But that's expensive and difficult to manage.
VLANs let you segment this network logically, creating virtual neighborhoods within a single physical switch.
It's like having separate secure spaces within the same building. This boosts security because traffic within one VLAN can't easily spill over into another.
It also improves performance by containing broadcast traffic within smaller groups.
This brings to mind the quiz question about how many IP subnets you need if all ports on a switch are configured as VLANs.
Yes. That one had me thinking.
That's designed to catch you out.
So what is the answer?
You can't tell from the information provided.
Really?
The quiz highlights a key distinction. VLANs and subnets operate at different layers of the networking model.
So they're not the same thing.
They work together, but they're not directly dependent on each other.
So to clarify for our listeners, even though you can't tell the number of subnets needed just from the number of VLANs,
they're both essential parts of a well-designed network.
Absolutely. They both play crucial roles in segmenting and organizing network traffic, just at different levels. Now, apart from security and performance, the book lists several other advantages of using VLANs.
Improved network management, easier troubleshooting, greater flexibility in allocating resources.
Yeah.
It also allows for applying different security policies to each VLAN. For instance, you could have stricter firewall rules for the finance department's VLAN compared to the marketing department's VLAN.
Interesting. And you can even prioritize traffic based on VLAN membership, ensuring that time-sensitive applications like video conferencing or voice calls get the bandwidth they need.
It's all about creating a network that's not just connected, but intelligently structured and tailored to your specific needs.
Now, what happens when devices in different VLANs need to communicate? We can't keep them completely isolated, can we?
That's where VLAN trunks come in. These are like specialized links between switches that carry traffic from multiple VLANs. Think of them as the bridges connecting our virtual neighborhoods.
Instead of having a separate physical link for each VLAN,
which would be a wiring nightmare,
we use trunks to efficiently transport traffic between them.
And this is achieved through a clever mechanism called VLAN tagging.
VLAN tagging?
VLAN tagging adds a special identifier to each frame, indicating which VLAN it belongs to. It's like putting a label on a package, ensuring that it gets delivered to the correct destination.
The book explains that this tagging process ensures that traffic from different VLANs doesn't get mixed up and that each frame reaches the intended recipient.
So we've got our network nicely segmented with VLANs.
And we're using trunks to connect them.
But what happens when we introduce redundancy into the mix? We want multiple paths for data to travel in case one link fails. But this creates a potential problem. Loops. Loops are a network administrator's worst nightmare. Imagine a data packet entering a loop. It would just keep circulating endlessly, consuming bandwidth and disrupting the entire network.
It's like
a traffic jam caused by cars going around in circles.
That's where our next superhero enters the scene. The Spanning Tree Protocol.
Or STP.
This protocol acts like an intelligent traffic cop, analyzing the network topology and strategically blocking certain ports to prevent loops from forming.
The quiz asks about the stable states a port can be in after STP has done its magic. Those states are forwarding and blocking. Forwarding ports are like green lights, allowing data to pass through, while blocking ports act like red lights, preventing traffic from entering a potential loop.
But how does STP decide which ports to block? It seems like a complex decision to make.
It is. STP uses a distributed algorithm where switches exchange messages called BPDUs.
BPDUs.
Each switch tries to become the root bridge, which is like the central authority in the spanning tree. The switch with the lowest bridge ID wins.
Hold on, bridge ID. What does that even mean?
It's a combination of a configurable priority value and the switch's MAC address.
So like an election.
Think of it as an election where the switch with the lowest number wins. Once a root bridge is elected, all other switches determine their role in the spanning tree based on their distance from the root.
Okay, so they figure out the best paths for data to flow, and any redundant links that could cause a loop are blocked.
This process of STP analyzing the network and establishing a loop-free path is called convergence.
Now, the book mentions that convergence can take some time, especially with older STP standards. What are the implications of this delay?
During convergence, the network might experience temporary disruptions or inconsistencies in data flow. It's like waiting for the traffic lights to synchronize after a power outage.
RSTP.
RSTP, or Rapid Spanning Tree Protocol, was introduced to address this issue.
So RSTP is like STP on fast forward.
Exactly. It significantly reduces convergence time, minimizing those disruptions.
Yep.
The book goes into detail about how RSTP achieves this, but the key takeaway is that it's designed for faster recovery and more dynamic network environments.
Okay, so we've established a loop-free network with STP. Are there any other tools or techniques we can use to further enhance our network's resilience and performance?
There are. The book delves into some optional STP features like port fast, BPDU guard, and loop guard. These are like specialized tools that provide finer control over STP behavior and add an extra layer of protection.
Okay, so for instance,
port fast allows access ports connected to end devices, like computers, to transition quickly to the forwarding state, bypassing the usual STP delays. This is because these ports are unlikely to be involved in loops.
It's like having an express lane for devices that don't need the full STP security check.
Then we have BPDU guard. It disabled STP on a port if it receives BPDUs. This prevents rogue devices or misconfigurations from disrupting the carefully crafted spanning tree. Think of it as a security guard protecting the network from unauthorized access.
And
finally, loop guard prevents a specific type of failure that could cause a loop even with STP enabled. It's an extra layer of protection, ensuring that if a link goes down, it doesn't inadvertently create a loop when it comes back up.
So it's like a backup system for STP, making sure that even if something goes wrong, the network stays protected.
Exactly. These optional features provide a robust set of tools for fine-tuning your STP configuration and ensuring a stable and secure network environment.
Well, this has been a great overview of VLANs and STP. I feel like we've covered a lot of ground.
We have, but there's still so much more to explore.
Absolutely. Stay tuned, everyone, because in the next part of our deep dive,
we'll get into the nitty-gritty of implementing and verifying these configurations.
Get ready for some real-world scenarios and practical tips.
I'm already excited.
Me too. See you then. Welcome back to What's Going On in the Internet. I'm really excited to jump into the practical side of VLANs and STP.
Me too. Theory is great, but actually implementing these concepts is where the real magic happens.
Exactly. Let's shift from the what to the how. Our trusty guide, CCNA 200-301 Official Cert Guide, Volume 1, dives deep into the nitty-gritty of configuring VLANs on Cisco switches.
Now, I remember this being the part where I got totally lost in the sea of commands. How can we break this down for our listeners, especially those who might be new to Cisco iOS?
Great point. It's not about memorizing every single command, but understanding the logic behind them.
Think of it like
learning a programming language.
You don't need to know every function by heart, but you need to grasp the syntax and the principles.
The book starts with the fundamental concept of assigning VLANs to specific interfaces on a switch. It uses the term access port for interfaces connected to end devices.
Like computers or printers?
So each access port can belong to a specific VLAN. It's like assigning a room to a particular neighborhood in our university campus analogy.
Precisely. And if a computer is plugged into an access port assigned to VLAN 10, it can only communicate with devices on that same VLAN 10.
Now, we talked about the default VLAN earlier, VLAN 1. The book reminds us that all ports on a Cisco switch are initially assigned to this default VLAN.
It's important to remember that for better security and organization, we need to create new VLANs and reassign those ports as needed.
This is where those Cisco IOS commands come in. But before we get lost in the command jungle, let's emphasize that the book provides a clear, step-by-step process for creating, naming, and assigning VLANs. It even includes a handy configuration checklist so you don't miss any crucial steps.
That's a relief. I always get nervous about messing up configurations. It's like having a recipe to follow. And just like with a recipe, you can always double-check your ingredients. Or in this case, your configurations.
Speaking of checking, once we had our VLAN set up, how do we verify that everything is working as expected? I wouldn't want to assume everything is fine and then run into problems later.
Excellent point. The book highlights the show VLAN brief command as one of the essential commands for VLAN troubleshooting.
And what does that do?
This command gives you a concise summary of all configured VLANs on the switch, listing their VLAN IDs, names, status, and the ports assigned to them.
It's a quick way to get a snapshot of your VLAN configuration, like looking at a map of our university campus with all the neighborhoods clearly marked.
Exactly. And if you want even more detailed information about a particular VLAN,
you can
use the show VLAN aid command, replacing aid with the specific VLAN number you're interested in.
This command is like zooming in on a specific neighborhood on our map. You get the lowdown on its type, MTU size, parent VLAN if any, spanning tree information, and a bunch of other details.
Now we can't forget about our trusty VLAN trunks. These are the superhighways that allow traffic from multiple VLANs to travel across a single link.
And the book dedicates an entire section to configuring these trunks,
emphasizing the importance of using the correct switch port mode commands to configure those interfaces as trunks, rather than just access ports.
Right. If we stick with our city analogy, configuring a trunk is like marking a road as a highway. It signals that this road is designed to handle traffic from multiple neighborhoods.
The book highlights different options for setting the trunking mode on a Cisco switch. We have statal trunking, where you manually define which VLANs are allowed on the trunk, and then there's dynamic trunking, which uses a protocol called DTP, or Dynamic Trunking Protocol, to negotiate the trunking parameters.
Dynamic trunking sounds more flexible, but potentially more complex to manage. Are there any security concerns we should be aware of?
That's a great question, and you're right to be cautious. While dynamic trunking offers more flexibility as it allows switches to automatically figure out whether or not to form a trunk,
It's crucial to
understand the implications of DTP and configure it carefully. Misconfigured DTP can lead to security risks or unexpected behaviors. It's like leaving the city gates open without proper security checks. Someone could sneak in and wreak havoc.
So, while dynamic trunking might seem convenient, it's important to weigh the risks and benefits and make sure you have proper security measures in place.
Now, there's another important concept related to trunks that we need to discuss.
Which is it?
The native VLAN.
The native VLAN. This is the VLAN assigned to untagged traffic on a trunk link. By default, it's VLAN 1 on Cisco switches.
But it's generally recommended to change this to a different VLAN for security reasons.
Why is that? What's so bad about leaving it as VLAN 1?
Leaving the native VLAN as VLAN 1 can create a security vulnerability. A malicious user could potentially inject untagged traffic onto the trunk and gain access to devices on the default VLAN.
It's like having a backdoor entrance to our city that anyone can use. Not ideal for security.
So changing the native VLAN is like changing the locks on that back door, making it much harder for unauthorized access.
Okay, so that makes sense. The book explains how to configure the native VLAN using the switchport trunk native LAN command. It also warns about the potential pitfalls of having mismatched native VLANs on either end of a trunk.
Mismatched native VLANs can lead to all sorts of network chaos.
It's
like having two cities trying to connect their highways, but their lanes don't line up.
You'll have
traffic jams and accidents.
That's a great analogy. So far, we've mostly focused on data traffic. But what about situations where we need to carry both data and voice traffic on the same network? Many organizations use IP phones,
which rely on the network for both voice and data communication.
Excellent point. The book dedicates a whole section to that, implementing interfaces connected to phones. It highlights how the rise of IP telephony has changed the way we think about network design.
Back in the old days,
PCs and phones had their own separate cabling and connections. But with IP telephony,
we can converge both voice and data traffic onto a single network cable.
This simplifies infrastructure and reduces costs.
It's like having one transportation system for both cars and buses. instead of separate roads for each.
Exactly. And to handle this converged traffic,
We use a combination of VLANs and a feature called voice VLAN,
it's like having dedicated lanes on our highway for different types of vehicles.
ensuring smooth and prioritized traffic flow.
The book outlines the steps for configuring these data and voice VLANs on Cisco switches.
It emphasizes the importance of using the switchport voice VLAN command.
This tells the switch.
This command tells the switch to treat traffic from the IP phone differently, prioritizing it for better voice quality.
So we're essentially creating a VIP lane for our voice traffic, ensuring it doesn't get stuck in traffic with the regular data packets.
Precisely. And when you configure a port with both a data VLAN and a voice VLAN, Cisco iOS automatically adds the voice VLAN to the list of allowed VLANs on the trunk, so you don't have to manually add it yourself.
Now, after all this configuration work, we need to make sure everything is functioning as expected. How do we go about troubleshooting VLANs in trunks?
The book provides several handy commands and techniques for troubleshooting these configurations. For example, the show interface's trunk command is particularly useful for verifying the status of our trunk links.
It shows us which VLANs are allowed on the trunk, the native VLAN, and the encapsulation method being used. It's like inspecting our highway to make sure the lanes are correctly marked and the traffic is flowing smoothly.
And if you suspect there might be a problem with a specific VLAN,
You can use
the show interface's interface on UD switchport command.
This command shows you the detailed configuration of a specific interface, including its VLAN assignment and trunking status. It's like checking the registration details of a specific vehicle on our highway.
All of these commands are crucial for identifying and resolving common VLAN and trunk issues, such as mismatched native VLANs, incorrect trunking configurations, or VLANs that are not properly assigned to ports.
They're like our diagnostic tools for keeping our network traffic flowing smoothly and efficiently.
Before we move on to STP,
Is there anything else about VLANs that you think is particularly important for our computer science students to grasp?
I think the key takeaway here is that VLANs are a foundational concept in networking. They're a crucial tool for improving security, optimizing performance, and simplifying network management.
Absolutely. Even if our listeners don't end up specializing in networking, having a basic understanding of how VLANs work can be incredibly helpful.
It's like knowing the layout of our virtual city. It makes navigating and troubleshooting so much easier.
Well said. Now, are you ready to tackle the complexities of spanning tree protocol in part 3?
Bring it on! I'm ready to conquer those loops.
Welcome back to What's Going On in the Internet for the final part of our deep dive into VLANs and STP.
I'm feeling like a network ninja in training already.
We've covered a lot of ground, but you're right, there's still one crucial piece of the puzzle left. Understanding why preventing those network loops we talked about is so important.
Okay, so we know STP stops those data packets from endlessly circling around the network. But what's the big deal? What kind of havoc can these loops actually cause?
Well, imagine a data frame gets trapped in a loop. It would continuously circulate through the network, replicating itself with each cycle.
So it's not just one packet causing trouble, it's like a whole army of clones.
Exactly. And this endless circulation consumes valuable bandwidth, leading to network congestion and performance degradation. It's like a denial of service attack, but caused by the network itself.
That sounds like a major headache for anyone trying to use the network.
It is. It's like
trying to have a conversation in a crowded room where everyone's shouting. But it's not just about bandwidth consumption. Leaps can also mess with the proper functioning of network devices.
the book specifically mentions how loops can disrupt a switch's MA's address table.
Which is essential for efficiently forwarding frames.
Right. Switches use MA address tables to keep track of which devices are connected to which ports. But when there's a loop, these tables become unstable and inaccurate.
Because the switch keeps seeing the same frame coming from different ports, right?
It gets confused about where the device is actually located.
Precisely. This leads to misrouted frames, lost data packets, and a generally unreliable network. It's like trying to deliver a package, but the address keeps changing every time you look at it.
So it's not just slow performance.
It's potential data loss and complete chaos.
You got it. The book breaks down the problems caused by loops into three main categories: broadcast storms, M-MAKI table instability, and multiple frame transmission.
Okay, let's unpack those.
It's a broadcast storm.
A broadcast storm occurs when a broadcast frame, which is meant for all devices on the network, gets caught in a loop.
Causing it to.
This causes it to replicate endlessly, flooding the network with copies of the same frame.
No.
It's like sending a mass email that keeps replying to itself, creating thousands of copies.
Exactly. This overwhelms devices and cripples network performance. Then we have AMI table instability, which we already discussed. The constant updates and incorrect entries caused by looping frames make the switch's forwarding decisions unreliable.
And multiple frame transmission.
That sounds like a recipe for duplicate data.
It is. When a single frame gets delivered multiple times because of a loop, you end up with duplicate data, wasted bandwidth, and potential application errors. Imagine receiving the same email a dozen times. Annoying, right?
More than annoying, it could actually cause problems if an application tries to process the same data multiple times.
You're absolutely right. So, to sum it up, STP is crucial for preventing these loop-induced disasters. It's like having a safety net to ensure smooth and reliable data flow, especially as networks grow larger and more complex.
As we discussed earlier,
It achieves this by strategically blocking specific ports to enforce a loop-free path for data.
now the book also mentions something called STP convergence time. What exactly is that?
Convergence time is the time it takes for STP to analyze the network and establish that loop-free path after a change occurs, like a link failure or a new switch being added.
So it's like the time it takes for the network to reroute traffic after a road closure.
A perfect analogy. And during this convergence period, the network might experience temporary disruptions. That's why minimizing convergence time is so important.
Which is where?
Which is where RSTP, or Rapid Spanning Tree Protocol, comes in. It's designed for much faster convergence than traditional STP, reducing those disruptions.
The book goes into detail about how RSTP achieves this. One key feature is the use of point-to-point links. RSTP assumes that most links in modern networks connect only two devices as opposed to shared segments like hubs. This allows RSTP to converge faster because it doesn't need to go through the same lengthy listening and learning states required for shared segments. It's like knowing you're on the right track because there's only one road to take.
Another RSTP advantage is
its ability to quickly transition ports to the forwarding state using something called edge ports.
edge ports.
Edge ports are those directly connected to end devices, like computers or printers. These devices typically don't participate in STP, so RSTP allows these ports to bypass the usual delays and transition quickly to forwarding.
It's like having an express lane for those devices that don't need the full STP security check.
Exactly. RSTP also introduces alternate and backup roles for ports, which further enhance its responsiveness to network changes.
It's all about speed and efficiency.
But even with all these improvements, the book emphasizes that RSTP is still backward compatible with traditional STP.
That's great for interoperability.
So you can have RSTP-enabled switches coexisting with older STP switches in the same network. RSTP will simply revert to its STP-compatible mode when interacting with those legacy devices.
It's like being able to speak both modern and ancient Greek. You can communicate with everyone, regardless of their dialect.
Okay, so we've got the theory down. Now let's talk about how to actually configure STP on our Cisco switches.
The book provides a comprehensive guide to configuring various aspects of STP.
You can set the STP mode,
whether PVST, Plusword, Rapid PVST, or MST, based on your network's needs.
You can also adjust switch priority to influence the root bridge election. Remember, the switch with the lowest priority wins. And you can even tweak port costs to fine-tune the STP path selection.
It's like having a set of controls to fine-tune the traffic flow in our city.
Exactly. And remember those optional features we talked about?
Like port fast, BPDU guard, and loop guard.
The book explains how to configure those as well.
So
we have a lot of control over how STP operates in our network.
We do, but as I mentioned earlier, with great power comes great responsibility.
Misconfigurations can lead to unexpected behavior and network instability. So thorough testing and verification are crucial.
Absolutely. Now, before we wrap up, let's revisit the concept of redundancy. We've talked about how STP protects us from the negative consequences of redundant links.
Those loops?
But there's another technique that actually leverages redundancy to our advantage. Yes. EtherChannel, or link aggregation. It allows us to bundle multiple physical links between switches into a single logical link.
It's like combining multiple lanes on a highway to create a superhighway with increased capacity and redundancy.
Exactly. EtherChannel not only increases bandwidth, but also provides fault tolerance. If one physical link within the EtherChannel fails, the remaining links can continue to carry traffic seamlessly.
It's like having a backup generator that automatically kicks in if the power goes out.
The book explains how to configure EtherChannel both manually and dynamically.
With manual configuration,
you explicitly define the links that should be part of the bundle. With dynamic configuration, protocols like LACP or Link Aggregation Control Protocol automatically negotiate and manage the Ether channel.
And just like with STP, the best choice depends on your network's specific needs and the capabilities of your switches.
And there you have it.
We've reached the end of our VLAN and STP journey. We started with the fundamentals, explored the potential pitfalls of loops, and discovered how STP and RSTP act as our network guardians. We also delved into the practical aspects of configuration, troubleshooting, and even learned how to leverage redundancy to our advantage with EtherChannel.
I feel like I've gained a whole new level of understanding.
Me too. And I hope our listeners feel empowered to apply this knowledge to their own networking projects. Remember, this is just the beginning. The world of networking is vast and ever-evolving. But with a solid grasp of these fundamental concepts, you're well equipped to navigate its complexities. So keep exploring, keep learning, and don't be afraid to experiment. And who knows, maybe one day you'll be designing the next generation of high-performance, ultra-secure networks.
Thanks for joining us on the Deep Dive.